Alright, I want to just give you some more examples of frictions. Couple of them may be the same examples I did in lecture. I just want to re-emphasize them and can just redo them because they are important. And one example, I want to introduce a couple more terms and which are sort of important when we're looking at friction. So let's go and use this particular example, 8.6, to introduce two important concepts or definitions. The first one is called, let me get the pen back. The first one is called angle of friction. And the angle of friction is defined tangent of theta as the static friction coefficient. The second one is called angle of repose. And this is defined as the maximum angle that you can have to lift the incline so that the block can start, its motion will be pending. In this particular case, the angle of repose is directly associated with the angle beta. So we might say in this particular example, its application is that beta is got to equal to Bs. Okay? So, and if you're interested, we can talk a little bit more about how this works. And I will also post a solution of this particular problem on Blackboard so you can better understand it. You will not have this sort of problem on the final, but I just want you to be aware that as friction problems can get a little bit more complex and difficult, and these two important angles are something that you'll need in order for you to solve some of the more complex and difficult friction problems. Like what we said in class, before you do any problem, the first thing that you have to do is sketch the free body diagram. So that's what I'll do. In this particular example problem, the free body diagram is actually fairly simple. You have the force P at the incline angle beta, my weight, which is 25 times 9.8, 245 Newton, my normal, and in this case, the impending motion is up the incline, therefore my friction is down that way. I'm going to set my coordinate axis to be x incline and y prime in the same direction as incline, and I'm now ready to set up my forces. My summation of the forces of x is equal to 0, therefore, or x prime, I'm going to have P friction. Sorry, this is 30 degrees. That's my weight. Minus 245, 730. Equal to 0. Summation of my forces in the y prime equal to 0. So I'm going to have P sine theta minus friction. Okay, no friction now. What I'm talking about. Plus normal plus P, sorry, the P. Minus weight 245 times 30. Equation 1. Equation 2. My third equation is my friction is going to equal to mu s times n. And my fourth equation is my beta is got to equal to phi sub s. And we know that tangent phi sub s is equal to my mu s. Okay? How many equations and how many unknowns do I have? I have 4 equations and 4 unknowns. My unknowns are my normal, my p, my beta, and my ds. So I should be able to solve for everything at this particular point. And if I go ahead and simply use equation number 4 to solve for ds, I can say my phi s is arctangent of 0.25, and that is equal to 14.04 degree, and that is equal to my beta. And once you have beta, you can go ahead and solve for the rest. You can do the math, and I'll tell you what the answer of P is. P ended up being 170.5. Okay, let's now kind of backtrack a bit and explain what are exactly the angle of friction and angle of repose. Okay, let me go ahead and explain that a little bit better now. Now we've done the math. So, let's see what I want to do. Let me go ahead. Just add a blank slide here, and I'm going to try to explain what is angle of friction. Oops. If you have a block sitting on a plane, here's my weight, here's my normal, and I'm going to start dragging or pushing it. Let's say we push it with the force P. Okay? What's going to happen? The y component of the P is going to increase my normal. My normal is going to equal to W plus P1, right? And here's my friction. My friction is going to equal to Px until impending motion. In that case, my Px will equal to mu s. Yeah. So let's say what happened to the free body diagram and impending motion. So at this particular point, we're still at Px. Now motion is impending. We're pushing it down. This is impending motion, P. So my n is going to equal to Py plus W. And this is now mu s n. Can you now see that in order for the motion to not move or not rotate, if all the forces will end up acting along a straight line, so let's say this is my summation of the forces of W and P, well actually the downward force and the upward force are such that all of the forces resultant pushing it down will be aligned with the resultant pushing it back up. Okay? And they go through the same line. This is what happens when motion is impending. We're not moving yet, right? The block is not rotating yet. The block is moving, so everything's got to stay in equilibrium. Forces got to be balanced. Moment's got to be balanced. And at this particular point, can you now see my mu Sn and here's my normal. Actually, let me write it over that way. My resultant is got to consist of my mu Sn, which is that force, and this is my normal force, right? That's my force triangle, and that makes up of that angle. But if this is mu Sn, this is n, you can see here's my angle. So my angle phi, or tangent of my angle phi, is equal to mu Sn. over n. That's mu x. Therefore, we call this the angle of the two.